I am Dr.P.Ambika, Assistant Professor, Department of Mathematics, Bishop College, Trichy, 17. I am going to take Euclidean algorithm in number theory. Now we are going to see divisibility of an integer. An integer a is said to be divisible by a non-zero integer b if there exists another integer c such that a is equal to bc. Here b is called a divisor or factor of a. We write b divides a. Thus b divides a if and only if a is equal to bc. For example, 3 divides 12 since 12 can be written as 3 times 4. Associates. Two integers a and b are said to be associates of each other if a divides b and b divides a. Division algorithm. For any two positive integers a and b, there exists a unique pair of integers q and r such that a is equal to bq plus r, where 0 less than or equal to r less than b. Common divisor. An integer a is said to be a common divisor of the integers b and c if a divides b and a divides c. Greatest common divisor. It can be shortly written as GCD or highest common factor, HCF. Both are one and the same. An integer a is said to be the greatest common divisor of the integers b and c if first one a divides b and a divides c. Second one, any common divisor d divides a. The HCF of two integers a and b is denoted by a comma b within the parenthesis. For example, HCF of 24 and 60 is equal to 12. The common divisors of 24 and 60 are 1, 2, 3, 4, 6 and 12. All these divisors divide the HCF 12. If the integer a is the factor of b, then HCF of a comma b is equal to a. For example, since 15 is the factor of 60, the HCF of 15 and 60 is equal to 15. Any two integers a and b have a unique HCF. Now we are going to see Euclidean algorithm. The method of finding the HCF of two integers is known as Euclidean algorithm. Let us take a and b be the two given positive integers. For convenience, let us take a greater than b. By division algorithm, we have a is equal to bq plus r, where 0 less than or equal to r less than b. Now we take r equal to 0. In this case, a is equal to bq. That means b is the factor of a. Hence, the HCF of a and b is equal to b. Suppose, let us take r not equal to 0. In this case, a is equal to bq plus r, where r lies between 0 and b. We take the HCF of a and b is equal to d, and the HCF of b and r is equal to d1. Now, the HCF of a and b is equal to d implies d divides both a and b. That means d divides a and d divides qb. Since d divides b, d divides the multiple of b. Since d divides a and d divides qb, that implies d divides their difference. That means d divides a minus qb. That implies d divides r, since r equal to a minus qb. From this equation, r equal to a minus qb. Thus, d divides b and d divides r. Hence, d is the common factor of b and r. But we have taken the highest common factor, HCF of b and r is equal to d1. and D is the common divisor of B and R, we have D divides D1. Also, the HCF of B and R equal to D1. That implies D1 divides both B and R. Since D1 divides B, D1 divides the multiple of B. That is, D1 divides QB and D1 divides R. Hence, D1 divides their sum, QB and R. That is, D1 divides QB plus R. But QB plus R is equal to A. So, we have D1 divides A. Thus, D1 divides B and D1 divides A. D1 divides B and D1 divides A. That means D1 is a common divisor of A and B. But we have taken the HCF of A and B is equal to D. And D1 is a common divisor of A and B. That implies D1 divides D. This is equation 2. So, from the equations 1 and 2, we find that D and D1 are the associates of each other. Hence, D is equal to D1. That means D is the HCF of A and B and D1 is the HCF of B and R. So, the HCF of A and B and R are equal. Now, we are applying the division algorithm repeatedly. We get A and B can be written as A is equal to BQ plus R, where R lies between 0 and B. Now, we take B and R, that can B is equal to Q1R plus R1, where R1 lies between 0 and R. Now, we take R and R1, that can be written as R equal to Q2R1 plus R2, where R2 lies between 0 and R1. And we take R1 and R2. R1 is equal to Q3R2 plus R3, where R3 lies between 0 and R2, and so on. Finally, we can write Rn minus 1 equal to Qn plus 1 Rn plus Rn plus 1, where Rn plus 1 lies between 0 and Rn. Also, we have proved the first part, HCF of A and B is equal to HCF of B and R. So that we can, so this is also true, HCF of AB equal to HCF of BR equal to HCF of Rn minus 1 comma Rn. Since R, R1, R2, etc., Rn, Rn plus 1 is a decreasing sequence of positive integers, a particular term in the sequence must be 0. Let it be Rn plus 1 equal to 0. So, we get Rn minus 1 equal to Qn plus 1 into Rn. That means Rn is the factor of Rn minus 1. So, HCF of Rn minus 1 comma Rn is equal to Rn. Hence, the HCF of A comma B is equal to Rn. Hence, the HCF of the given integers A and B is the last non-zero remainder got by the successive division algorithm. Here, Rn is the last non-zero remainder. We see one example. We have to find the HCF of 963 and 657. 963 can be written as 1 times 657 plus 306. Now, 657 can be written as 2 times 306 plus 45. Now, 306 is equal to 6 times 45 plus 36. Now, 45 is equal to 1 times 36 plus 9. Now, 36 equal to 4 times 9 plus 0. Here 9 is the last non-zero remainder. Hence, the HCF of 963 and 657 is 9. Thank you.